So thank you, Tanya, for the introduction, for all the organization. And thank you all for coming here. It really is great to be back here again in person. So let's go. 2 or 3 words about myself. I work at AMD on graphics compilers based on LLVM. And I've done so for about 7 years. And that experience does inform the talk that I'm going to give. But I really do want to take a broader perspective. Let's take a step back from the day-to-day and think about where can the LLVM project go over the next, 10 years, let's say. And when I say the LLVM project, mostly I really do mean the literal LLVM project repository and all the development that happens around it. And when I say LLVM and MLIR, I mean mostly the corresponding subdirectories. And so this project is extremely big, right? We have 375 people here, as Tanya said. There isn't one person who can keep everything that's happening in this LLVM project in mind. And so one thing that's very important is communication between us humans, but also communication between different parts of the code that we're working on, the interfaces between the pieces of code. And of course, the way that compilers communicate amongst themselves is intermediate representation. So I really want to take a deep look at how our intermediate representations look today and where they might go. So on this slide, I took a bit of a sampling of the sort of languages that we have today. And it might look a bit scary, but really the reality is in many ways less scary than that. In one part, because all these little languages that are shown here belong to really 3 language families. And so that helps. Speakers of 2 of those sub-languages still share the foundation of the language family. It is also not as bad as the slide might suggest because all this variety of languages is largely there for a reason, right? It reflects the inherent complexity of the problems we're working on. If you look there on the right, ARC64 really is different from x86 and really is different from RISC-V and so on. And if we were to try to shoehorn all that into one language, we would just actually increase confusion. So having this separation into sub-languages is actually a good thing. In some ways, though, reality is worse than what's on the picture there. So the picture doesn't show selection DAG, for example. And that's because I'm just quietly assuming that that's going to go away with global ISEL, so let's not speak of it. But in another way, so this little harmless rectangle of LLVM IR there in the middle really isn't just a little harmless rectangle. And really, we should blow it up into a whole bunch of sub-languages as well. This is already the case today to some extent when it comes to target intrinsics. But even for the target-independent intrinsics, there is room here to organize things better. Okay, conceptually, LLVM's rise to fame is largely connected to LLVM IR. But what is LLVM IR really? If you ask somebody, they might point you at a piece of textual IR, like here on the slide. Or they might remember, hey, we also have bitcode. Or if they're a bit more theoretically minded, they might say, we have this langref, this language reference manual that describes the instruction set, that describes intrinsics, attributes, all that good stuff, the semantics that go with them. And that is what is LLVM IR, this theoretical definition. Or somebody who is more practically minded might point at all the infrastructure that we have in terms of C++ classes that allow us to work with code in a live environment, do analyses, do transformations on it. And all of these are important aspects, but it helps to tease them apart occasionally. Right? And in particular, the 2 points there at the bottom, I like to think of them as what's really behind the notion of a dialect and what I'm calling the substrate. So dialects, of course, that's a term introduced with MLIR. And what I associate with a dialect is it's an instruction set, associated set of types, perhaps, semantics that go with them, the kind of thing that you would find in langref or maybe in a table gen description of a dialect of MLIR. And the substrate, on the other hand, is what allows us to concretely work with code in the C++ world. It is a set of C++ classes that together allow you to represent and transform code. So the LLVM substrate would be, in classes like LLVM instruction, LLVM value, basic block, and everything that's tied to that. And on the MLIR side, we would have MLIR operation, block, value, and so on. And the key insight, the really important insight that MLIR brought to the table is this notion that if you separate these two concepts, well, you can start thinking, actually, we can have many dialects within the same substrate, and that allows us to build cool technology. But also, you can, in a sense, have the same dialect on multiple substrates, right? We can think of LLVM IR theoretically defined as the LLVM dialect that exists on the LLVM substrate, but there is also the LLVM dialect on MLIR. And those are not entirely identical for practical software engineering reasons. It's just what do people care about, but they could be, right? And so when we see this picture, this is nice because it means we can move between substrates, right? But actually, substrates do matter quite a bit in software engineering reality because the code that we write, transforms, analyses, and so on, that code is tied to a substrate. We can represent LLVM code in MLIR substrate, but then we can't use all the good stuff that has been written over the years in LLVM in terms of transforms, loop optimizations, inst combine, all that good stuff. We can't run it on the MLIR substrate. There is a barrier here. And that barrier, that can become an issue. So here's an example from my own personal experience from our graphics compiler that starts with SPIR-V. And SPIR-V is really pretty much LLVM IR plus GPU-specific stuff on top. And so it operates at a level of abstraction where if you want to compile SPIR-V to binary code that actually runs physically on the GPU, it makes a lot of sense to reuse an LLVM-style optimization pipeline. But you do want to augment the code with certain custom operations that are GPU-specific, right? Like what you see in those red rectangles there. Those are custom operations that our graphics compiler, LLPC, defines and mixes with otherwise fairly standard LLVM code. And we can do that, of course, right? We can define these functions. They will never get a body. They will just be lowered away at some point in the compilation pipeline. But we don't have all the niceties that MLIR gives us for working with such custom operations. And so it would be really cool if we could be using MLIR in our compiler. But if we wanted to port it over, we would lose access to the wealth of analyses and transforms that LLVM gives us. So we're sort of, between a rock and a hard place here. And so it would be really great if we just had a single unified substrate as a foundation that everybody builds on. It would address this problem of interoperability that I just talked about. It would also help us eliminate a boundary to pass ordering in compilers that use both MLIR and LLVM. And what I think is also very important is it makes the project as a whole more accessible to developers, right? If you have somebody who focuses mostly on front-end concerns in a high-level compiler that's based on MLIR, and somebody who is more familiar with middle-end development, it would be easier for them to talk with each other if they worked on a shared substrate from day to day. And a single person could move more easily between front-end and back-end if there was a single substrate. Okay, so I think unifying LLVM and MLIR would be a really good idea. Before I talk more about that, let's reflect on how we got to where we are now. When MLIR wasn't introduced for inclusion into the LLVM project a couple of years ago, there were some people, myself included, who asked, hey, those are some really nice capabilities. Can't we add those to LLVM itself? And that's a nice thought. It would have been nice. But the software engineering reality was that MLIR needed to develop very rapidly. And LLVM was a fairly mature project at the time, was developing more slowly. So fast development here, slow development there. Trying to force MLIR into LLVM would have suffocated the project. So it was absolutely the right decision to add MLIR as a new substrate. But now we have a couple of years more experience. Maybe it's time to revisit this question with a fresh eye. And to be clear, what I'm talking about here would be an absolutely massive project, right? Absolutely massive. But let's not be afraid. let's just say, it's a lot of work, but we're optimistic. How would we actually go about it? So thought experiment. I've drawn here on the slide a sort of abstract schematic of what a compilation flow looks like that starts with MLIR all the way back to code gen. And so there's an MLIR front end, there's an LLVM back end, and I've illustrated here what are the passes that are run on the code as it's being transformed, what are the dialects that are in use, and what are the substrates that the passes operate on. You'll note that the passes are tied to their substrate. They're always the matching color here from left to right. The dialects are a bit more flexible, right? We start with various high-level dialects in the MLIR world. At some point, we go to the LLVM dialect. And we go to the LLVM dialect while still being in the MLIR substrate. And so if you look at this picture, one plausible thought that you might have is to say, hey, why don't I start there at the left and just port passes one by one from LLVM to MLIR? Right? Seems plausible, and if we do that for a couple of passes, we end up with a picture that looks like this. Okay? We still use the same dialects in the same places, but where previously we have used the LLVM dialect on the LLVM substrate, we're now using the LLVM dialect on the MLIR substrate in a couple of places. There is an interesting question here of, do we still talk about the LLVM backend covering the same interval here? And one can quibble over that, but it seems like a plausible approach, right? We could continue doing this from left to right until eventually the LLVM substrate just disappears. Okay, cool idea. Reality check. So this is the -03 optimization pipeline. And first impression, please don't try to read it all. Obviously, we're talking about a lot of work here. But we knew that, and we said we're not afraid. The more critical point is, after about 5 passes, we hit simplify CFG. And simplify CFG appears 8 times in the compilation pipeline. So, okay, we're porting simplify CFG to the MLIR substrate. And that's good for the first instance where it appears. But then what about the other 7 instances? What happens there? So really, the picture from the previous slide needs to be corrected slightly. There are these passes, and I've indicated that with the little dots there, where the same pass appears multiple times in the pipeline. And so once we have ported it, we have, in a sense, ported it for all these instances where it appears. So what does that mean now? One way we could deal with this is that, so we've ported simplify CFG, that's great for the first instance. After that, we still go back to the LLVM substrate. Then we hit simplify CFG again. Well, we've ported that, so let's convert again to the MLIR substrate. After simplify CFG, go back to LLVM. And we do that a couple of times. And of course, we could do that. But clearly, there's a compile time cost that I'm sure many people wouldn't be too happy about. The other thing we could do is to say, we ported simplify CFG, but nobody forces us to delete the old version. Right? We could just keep one version around for LLVM. We could keep one version around for MLIR. And that's also possible, but of course, that has a maintenance cost. If you think about the kind of large-scale transitions that we're doing in the LLVM project, stuff like opaque pointers, new pass manager, global ICEL, these projects take years. And are we really prepared to have the maintenance cost of having a whole lot of duplicate passes for all these years? Not just talking about simplify CFG here, talking also about inst combine, which is gigantic, talking about things like alias analysis and so on. We could do that, but we need to be careful about the cost we're potentially incurring. Is there something else we could be doing? So here's a second thought experiment. Can we make code be generic over the substrate that's being used? We already do that in some select few places, right? Dominated tree analysis is written to be generic over the substrate because it only really looks at the graph, and so it's a template parameterized over the node type, and that works, and everybody's happy. And so maybe this technique could be extended. So here I've chosen some random small helper function that exists in LLVM today. And today in LLVM, this is a non-template function, right? It has basic block pointer, it has instruction pointer as arguments. We could turn that into a template, right? And we could keep doing that for more and more code, and maybe at some point we're at the place where we could even do this. Now that would be pretty cool, right? Like just unifying by aliasing. And you know, there is some plausible stuff here, but again, reality check. This is the body of that function that I chose. And you know, I chose a simple function for a reason. It does the obvious splicing at the bottom that you would expect from a function that's supposed to hoist instructions, but it also touches debug info. And so this function we could turn into a template. That's actually not a big problem, right? That's just a little bit of syntactic manipulation, and there you go, it's a template. The problem is that you cannot use this template on the MLIR substrate, because it uses a whole bunch of methods that just don't exist in MLIR. And some of them don't exist for small reasons, like at the bottom there, you know, LLVM basic block has a getInstList method. MLIR block has a getOperations method. They do the same thing, maybe we can agree on a common name. But there are a whole bunch of methods here that are being used that refer to debug info and that are implicitly tied to how the LLVM substrate thinks about debug info. And the MLIR substrate thinks about debug info in a slightly different way. So, you know, something would have to be done there. And of course, you know, there is a free function call here, and this free function that's being called would also have to be turned into a template, so you ask the same questions then recursively. So that's a challenge. Okay. There is another issue with writing template code. You know, personally, I don't like writing template code, especially big templates, because tooling for templates is just weak, right? A big fan favorite is that error messages are often bad. Compile times can also be a worry. Maybe not so much here, because I'd expect us to use a lot of explicit instantiation, which helps. But to me, what the biggest issue is with writing large-scale templates is that language server functionality is just almost not there when you're writing template code. So the example here is from the previous slide. You know, in the non-template version, I get a nice tooltip with the comment of the method, and in the template version, I don't. So that's painful. There is some hope there, though. You know, what if we were to use C++ concepts? It is a plausible idea, right, to say if we want to turn things into templates, let's define a concept of what is a block. Let's define a concept of what is an instruction, a value, and so on. And then, you know, if we write our templates in those terms, then maybe that helps tooling. We can't do that today because it's a C++20 feature, but our time horizon here is like, I don't know, 10 years. In approximately 3 years, I expect we will be able to use concepts. You know, maybe tooling gets better. It's sort of bad that C++ concepts are kind of just slightly not the right design to really help tooling a lot. You know, something like traits or type classes would be better. But maybe they're close enough that there is hope that over a couple of years we get similar, you know, tooltips and completions and so on if we write templates with concepts. The other thing is that thinking of this in terms of concepts gives us an interesting tool for thinking about the problem of unification of the substrates. So if we define a basic block concept, we can start small, with small amount of functionality in that concept, and then gradually expand it. We would surely start with CFG predecessors and successors, because that's what's already being used today by dominated tree analysis and so on. We can expand it to cover iterating over instructions and stuff like that. At some point, maybe we can expand it to include basic block arguments. But LLVM uses phi nodes. That's interesting, right? Nevertheless, you can imagine how over time one could expand this concept and work towards making the substrates more similar to each other. And the This leads me to what I call the delta matrix that I promised before, which, if you're remembering one picture from this talk, I would like it to be the one that is developed on this slide, which is a way of thinking of, okay, we aim for unification of the LLVM and MLIR substrates. What is all the work that we would have to do to get there? Where are the differences between the substrates? What are the pieces of code that are affected by the differences in the substrates? And so we can think of this really as a two-dimensional matrix along the lines of those two thought experiments we ran, right? The first thought experiment was port one code artifact after the other, and that corresponds to the rows of the matrix here. Right? The rows are the pieces of code that are affected by the differences in substrate. Clearly, the front ends are examples of that, transforms, analyses, infrastructure like the IR linker, tools like LLDB and the JIT infrastructure in general, and so on. And then the columns of the matrix is the other dimension that corresponds more to the second thought experiment. Those are the conceptual differences between the substrates. Okay, so the first column there says constants. Well, LLVM uses constant value objects. MLIR uses instructions for materializing constants. MLIR allows an instruction to define multiple values. In LLVM, we have to fake it with structs. LLVM uses fee nodes. MLIR uses basic block arguments. The builder interfaces are different. So all of these differences, conceptual differences, are placed into the columns of the matrix. And so then the cells, you can think of the cell between simplify CFG as the row and fee nodes versus basic block arguments as a column. That cell represents the effort we would have to make for unification caused by the fact that simplify CFG looks at fee nodes and MLIR uses basic block arguments. And so those two dimensions correspond to two different approaches for attacking the delta, right? We can say we port simplify CFG, as we discussed. And once we have done that, modulo the question of code duplications, we can strike out that row from the matrix, and the matrix becomes smaller, the delta becomes smaller. We can say, let's tackle a column. Let's port LLVM to use basic block arguments. Okay, and after we've done that, we can strike out that column, and all subsequent porting efforts of rows become easier because they at least no longer have to deal with that particular problem. Right, and so this gives us ways of thinking about the problem of unifying the substrates, and that's really the key here, right? I mean, I hope we all have fun working on LLVM or the project overall, but at the end of the day, there should be some delivery of value in terms of writing compilers, right? And I think this idea of unification has the potential of giving us a lot of value, but it happens on a very long-term timescale. And that's difficult for motivation, difficult for funding, difficult for project management. What we should be doing is to try to break it up into small steps that lead us in the right direction, and that each can deliver value on a near-term basis, right? Because that's the way to motivate people to work on some of those things. And now, I'm actually quite optimistic. I mean, this is a huge effort, obviously. I mean, I'm repeating myself. But I'm quite optimistic about this idea of column refactorings. I mean, both approaches, I expect, will be used. But this refactoring is something that interests me in particular. And so for the last part of my talk, I want to pick out some examples and talk about those. What's involved, what is the value we can get out of it, and so on. And as the first example, I want to look at this idea of having dialects as an explicit thing in the LLVM substrate, which in many ways is sort of foundational for a lot of this unification project. And when I say dialects in LLVM, what are really the things that I mean here, that correspond to kind of the pain points that we have today? Well, the first one is to have first-class support for extended instructions and types. Ideally, defined in a way that is perfectly compatible with MLIR. Like the vision would be that you define the types and instructions and so on of a dialect once, in a TableGen file, in assorted C++ files, and then compile them once for the LLVM substrate and once for the MLIR substrate. That would be awesome. That's probably not what we'll be able to do very quickly, but it's good to keep in mind as sort of a guiding light. The second is this cleanup of LLVM as a language. And finally, exposing extensibility to front ends to leverage these capabilities as well. And so first-class support for instructions and types that are defined in an extended way. What do I mean by that? Well, we have a way of defining, in a sense, custom instructions in LLVM today, which is intrinsics. But in many ways, intrinsics are second-class citizens, and not necessarily for very good reasons. I mean, just if you look at them in textual IR, they look kind of bloated there, if you just look at the comparison. That would be nice to fix. They are second-class citizens when it comes to working with them in C++ code, right? If you have an instruction in your hand and you're asking, is that a store? And if so, I want to do something with its pointer. On the left side, that looks like fairly nice code, right? You use a dynamic cast, you have a get pointer operand method, that's cool. On the right-hand side, what if the instruction might be a prefetch intrinsic and you want to work with its pointer operand? That looks way less nice, right? And in some cases, for certain intrinsics, people have been addressing this issue manually. You know, for memcopy and memset, there are these, I'm not sure what to call them, but they're sort of veneer classes that help integrate them into the casting infrastructure and that provide nice accessor methods to get at the operands. But we know from MLIR that we can be doing better. We can auto-generate a lot of that stuff, for example. And finally, intrinsics are, once we care about compile time, are often less efficient than native instructions. So the example here is that a store instruction can be volatile, and that's just a single bit in the memory representation of the instruction. A memset can also be volatile, and that's an operand. So then you have to pay the cost of the entire operand in memory. Accessing it is slightly more expensive. And these are small things, but if you have intrinsic heavy code, they do add up. And all of these seem to me fairly realistically addressable within the context of LLVM. There is the point about just cleaning up the langref. That's a callback to one of the earlier slides. Langref.rst is more than 27,000 lines of text. And if you see a source file with 27,000 lines, you'd think maybe we should split it up. I think that applies to langref as well. And keep in mind that actually a lot of these little sub-languages like the target intrinsics aren't even really documented. So, in reality, if we were to document everything properly, we would be way above those 27,000 lines. And finally, extensibility is also an issue that's dear to my heart. You can sort of extend LLVM without changing LLVM itself with your own intrinsic by defining a function whose name starts with LLVM dot. And then what happens is that LLVM will tell you, if you call that function, yes, it's an intrinsic instruction, and its intrinsic ID is not intrinsic, which just seems silly, and we should be able to do better, right? The intrinsic ID enum, why is that not extensible? That would unlock quite a bunch of value for external front ends. There is a question of, how do we break this up in small steps? But if you're interested in more here, I have a talk this afternoon called LLVM Dialects, where I talk a bit more about this first example here. The second example I want to look at is this column of constants. Right? On the left, we have the LLVM world, where constants are just constant value objects, and there is a whole class hierarchy of different constant value classes. Constant data, constant aggregate, constant expression, and so on. On the right-hand side, we have MLIR, where there are materialization instructions for constants. And so this whole class hierarchy just doesn't exist in MLIR. And when we see a difference like that, and we want to unify, the first question should be, well, how do we unify? Right? Which should be the unified design? For that, we need to look at the pros and cons, right? We need to have a discussion about that. On the left, the LLVM approach allows you to very easily compare constants for equality. On the other hand, the MLIR way of doing it has a bunch of benefits. For one, it makes extensibility easier. What do I mean by that? Well, if you write a dialect that defines its own types, most likely you'll want to define your own constants. If we have a hierarchy of constant value classes, then that means we need to provide an extension point in that hierarchy. If, on the other hand, we have materialization instructions, we can just reuse the extension point that is already there for instructions. So extensibility becomes easier with the MLIR approach. We can put debug info on constants. It actually helps with multi-threading. So if you think about, a bunch of users of LLVM would like to be able to do multi-threading within a single LLVM context. It would be beneficial in some JIT contexts. It would presumably help with LTO. But it's not possible today. And one of the big blockers is the use lists of constant value objects. And if we were to use materialization instructions, that part of the problem just goes away. So, reasonable people can still have different opinions here, but I personally land on the side of MLIR has the better design. If we unify, we should unify in that direction. And the question is, who would do this work? Again, who can draw value from that work? Like I said, maybe this is beneficial for some LTO use cases. Maybe it's beneficial for some JIT use cases via the multi-threading. Maybe somebody cares about having debug info on constants. And then, that might motivate people to chip in here. And in terms of how we actually go about it, well, we have to eliminate this whole sub-hierarchy of LLVM constants somehow. Nikita Popov did some good work recently of eliminating some constant expressions. We still have constant expressions in that hierarchy, and the main reason for that is that constant expressions can appear in global variable initializers. So clearly one of the steps we need to take is, do global variable initialization differently with some sort of standalone representation of constant data. Constants can appear in metadata, similar issue here. And when it comes to the standalone representation, again, there's a question of, well, what should that look like? MLIR can serve as an inspiration here. It has this notion of attributes. And that's a fairly solid design. Why not use that? The only issue with that is that why did it have to be called attributes, right? LLVM has something called attributes, and that's a very different thing. But maybe we don't copy the name and find a different name for it instead. But you get the picture. Then there is the sub-hierarchy under constant of global values. And clearly, we can't remove global values, but we can detach them from the hierarchy and refer to global values from code in a different way via some materialization instruction that refers to a symbol, let's say. Right? This is the MLIR approach, and it makes a lot of sense. And then finally, just remove the whole thing, replace every remaining uses by constant instructions. And even the sub-project, of course, is a project of decent size. But I hope I've at least illustrated to you how that can be broken down into gradual steps that can be done one by one. So it's not like one gigantic patch that drops on one day, but it's a refactoring that can take place over time, as long as we agree that it's a good thing and we find people who are motivated to do so. As a last example, I want to look at regions. So MLIR has this idea of regions of basic blocks that can be attached to operations, which is crucial for modeling structure control flow. That's the example there on the right. And of course, LLVM just doesn't have anything like it. So the relationship between functions and basic blocks in LLVM is a different one than it is in MLIR. And here the question of what should the unified design be is I think, pretty obvious. There's no way we're going to remove regions from MLIR. If we want to unify, we need to add them to LLVM. Why would we do that? Is there some near-term value that can be drawn from it? The answer is actually yes. There are some interesting uses, at least in the AMD GPU backend that I'm aware of. We have this thing that's called wave-wide mode. So for those of you who are a little familiar with GPUs, you probably know that if you have control flow, that control flow gets translated into masking of lanes, right? And in certain cases, for internal reasons, we break out in what we call wave-wide mode, where we temporarily turn on all the lanes, regardless of what the control flow is saying. If you've heard of ISPC, this compiler that for for writing SIMD code on a CPU in a way that's similar to GPU code, they actually have an explicit syntactic construct called unmasked that also does this. And so modeling this wave-wide mode in LLVM is really nasty. It gets really hacky because it just clashes completely with the regular control flow of things. So there's just no good way of integrating it into the control flow graph. And so that would be a great opportunity to say, we have an operation, wave-wide mode, and then it has an attached region, and what's in the region gets executed with all lanes enabled. Another use case actually also in AMD GPU, we have this thing called waterfall loops, and we don't need to go into the details, but the point is that those are highly regular loops that have a kind of loop condition that regular loop transforms just really can't do anything with. But if we represented them in a higher level way, then we could write certain optimizations more easily. And finally, maybe for front ends that emit LLVM, for languages that are kind of at the abstraction level of C, maybe even Clang itself, could we use regions for something like scopes and lambdas? Okay, so suppose we do this. How would we go about it? First thing, there is an LLVM region. It means something different. I would argue, let's just rename it, move it out of the way. And then we'll have to refactor this parent-child relationship between function and basic block by introducing the region in the middle. And of course, we'll have to touch quite a bunch of code when doing this, because every place it says bb get parent, now we'll have to think about, does that actually need the function, or does it only want the region? So we'll have to audit that. Maybe some of that can be helped with scripts. But there is a whole bunch of stuff to work through. And we should try to break it up. First remove the, maybe rename some things, introduce a bb get function, transition users to use that, and so on. We'll have to think about what happens with function passes. Should some of them maybe be region passes? Are some of them genuinely about functions? And as a last step, add a way. Now, once we have function, region, basic block as parent-child relations, then we can say, okay, now we add a way to add regions to instructions. So again, thinking about how to break these refactorings that are overall quite complex down into smaller, manageable pieces. Let me recap. What are sort of the key points that I talked about? Well, the notions of dialects and substrates, teasing those concepts apart is very powerful. I really think that going to a unified substrate would be a worthy goal. We've run through thought experiments of how we would actually get there. I've talked about this notion of a delta matrix as the conceptual framework for thinking about what would have to be done. And we looked at some of these example column refactorings about what kind of value could they deliver, how feasible are they, and so on. So, where does that lead us? Do I actually think that in 10 years we will have unified LLVM and MLIR? If somebody were to fund a focused effort, then I think it's very feasible. I'll stand by that. But without that, it seems optimistic. What I do think is that in 10 years, we can look back and say, look, we didn't manage to unify them. It's just a very big challenge. And it's a little sad, but it's okay. We have brought them closer together by then. And in doing so, we have improved LLVM, we have improved MLIR, and we have made the LLVM project as a whole better and stronger for the future. That's what I hope for, and I think that's a very realistic goal that we can aim for and that we should aim for. And with that, I'll leave you, and thank you very much for your attention.
Thank you, Nicolai, for your talk and for your call to action. We now have time for questions. Please come to the mics in the alleys or wave at me if you have a question.
Thanks, Nicolai, for the great talk. A quick question. It reminds me of something, the trying to get something like parallel IR into the LLVM IR, which eventually failed. One of the reasons was like once you add this parallelism to LLVM IR, all the parsers need to support it all at once. And I see like with this region one, once you add permit a region, all the parsers need to support regions all at once. And that seems like the very same problem. Like, how would you intend to solve that?
That is a big problem for the particular region case. Something to point out is that this sort of problem doesn't necessarily affect everything. So for example, if you start to introduce custom operations and a pass isn't aware of custom operations, we can fall back to treating it like a call to an unknown function, for example. And this exact question that you've asked, I have also struggled with. It is not entirely clear to me. I do think part of the solution is to tease apart, there are function passes and there are region passes. But yeah, at the end of the day, it is a big project.
Hey, Nicolai. Thanks for the talk. It was really great. I was a little afraid of it beforehand, but you did a great job. So let me start with that. So a lot of things in there are really great about the intrinsics, making them, more first-class citizens. That's great. Getting LLVM dialects seems like a reasonable idea. Well, let's go to that matrix that you had, where you're like, okay, you want this, eliminate the columns, get it closer together, and then you gave examples of, you give a few examples of things that it can have like short-term benefits for us, probably. So it's like, doable, and we get a benefit of it, and I kind of believe that. But there's probably a lot of columns in there where the opposite is going to be true. It's either going to be hard or we're actually going to incur a draw. Like we actually suffer from doing it. Like we're not going to win anything until all of the columns are gone. So how do we deal with those?
Yeah, I mean, the key part is start with prioritization, right? As you said, there are a lot of columns there that do plausibly give us a lot of near-term value. Start with those. In the meantime, I'm sure there will be good reasons to address some of the rows, right? It's not just about the columns. It's really about both approaches there. But you're right, there is a long tail, and I'm not aware of any specific difference that necessarily hurts us to address.
I mean, constants even could. I mean, the pointer equality might incur a compile time cost. I don't know.
That's fair. That's fair, and we need to carefully measure that.
Right.
And in a way, maybe this is even an opportunity, right? I mean, when MLIR was added, these sort of details were not looked into. What are the performance benefits? In some cases it's obvious, but in other cases, like the constants, it's true. It's not entirely clear. And so I'm definitely not saying we should rush that. In a way, by approaching it in a gradual way, it allows us to revisit these kinds of questions. And I don't have the answer to everything, obviously. It's 10 years, who knows? But yeah, we need to be aware of that and just take it a step at a time.
Thank you.
That is a good question, yeah.
Next question, please.
So I'm thinking about this kind of concept idea, and I wonder, in the future, which of those concepts are interesting to exist. So imagining a future where, let's say, there's only one substrate. Are those concepts still interesting to keep around, or are they just a stepping stone to get you to the point where eventually the concept goes away because you don't need it anymore? Or maybe to put it another way, I think some of the value in having like a concept like regions is that maybe you rethink the way that you capture some of these algorithms. And so just taking the same algorithm and shoehorning it into using a concept to abstract the differences between LLVM and MLIR maybe isn't the right thing. The value is actually in looking at the code and sort of doing this audit and saying, well, would I really think about the algorithm in the same way if I had to do it in MLIR versus LLVM or something?
Yeah, that's a very interesting point. So to the first part of your question, I would say that in a way it is an aid for the transition, And if we just magically could snap our fingers and have a unified substrate today, then we wouldn't really need those concepts for the software development part of it, except maybe block because some of those CFG analyses are also used on the Clang AST. But yeah, the conceptual rethinking of it is very valuable. We started doing this LLVM Dialects thing in LLPC, and we found a similar thing there that it helps us rethink what our custom operations are in that particular case, and actually make things better through the process of trying to put it onto a more kind of grounded base foundation. And I think the same could very well apply to algorithms on regions, like you said.
Thanks.
Okay, thank you again, Nicolai, for your talk. And thanks for all the questions. Let's thank the speaker again. The next talk.